Assalamualaikum and a very good day. So now we are in last week for applied mathematics course for this semester. We're still under Fourier series chapter, but today we'll go class to the full range Fourier series. For the full range Fourier series topic, at the end of this topic, you should be able to determine the full range Fourier series. So now class, we go to the concept of this full range Fourier series. You have to know about the formula. This formula no need to be remembered because it's already provided in mathematical formula book. So the full range Fourier series, the formula, for example, we have here ft is a periodic function with period t. So you have to know the period. What does it mean by period? For this one you have learned in week 12. Then the Fourier series of this function is given by the ft is equal to, we have here a naught over 2 plus the sum of starting from n equal to 1 up to infinity a n cos n omega t. So what does it mean by this omega? This one is angular frequency. You already learned about this angular frequency in week 12. So if you forgot about this, you have to refer back to the video of week 12. And plus bn sine n omega t. Where here a naught, an and bn are the coefficients of the Fourier series. So that to solve this one or to find the full range Fourier series, you have to find the coefficient, which is you need to find a naught, also an and also bn. And in this case, a naught is given by the formula 2 over capital T here. What does it mean by this capital T? It is a period, which is you have to integrate starting from negative t over 2 to t over 2, that function respect to time. And then for the an, actually we do the same way, we did the same way as a naught, but your function here you have to multiply with cos and omega t. And here this n should be equal to 1, 2, 3 up to infinity. And then for bn, you have to change the function instead of using cos. So for this bn, we will integrate the function of ft, we multiply with sine n omega t. And then here n also equal to 1, 2, 3 up to infinity. So class, before we go further to the example, you have to know the important part here. If we have sine function is odd function. So if you compute here sine negative n pi, which is n equal to 1, 2, 3, and so on, you can see when n equal to 1, okay, sine negative pi you got equal to 0. And n equal to 2, sine negative 2 pi you got equal to 0. Means that here we have inside this, okay, sine is negative n. So all here, when we have n equal to 3, 4, and so on, we will have sine negative value. All this will be equal to 0. And then sine n pi, okay, this one, when you compute, you also got equal to 0. Means that the sine negative n pi equal to 0 and also sine n pi equal to 0. And this sine is odd function. We will see later the important which part that we need to use for this information. And then class, for cos function is even function. And then if you compute here, we use the same way. We have cos negative n pi. You can see cos negative pi, you got negative 1. And then for this one, when n is not negative, when here is not negative, cos pi also you got equal to negative 1. And cos negative 2 pi you got equal to 1 here. And then cos 2 pi equal to 1. So this one, when we summarize, we got cos negative n pi equal to negative 1 to the power of n. And cos n pi equal to negative 1 to the power of n. Class, so now we go to this example 1. Given the following periodic function, we have here fx equal to 1 if x in between 0 and pi. And then fx equal to negative 1 if x equal to negative pi to 0. In this case, the question gives us fx equal to fx plus 2 pi. If you base on the previous video in week 12, this 2 pi is referred to the capital T, which is it is period. Means that in this case, the period for this function is equal to 2 pi. And then you need to sketch fx, and also you need to determine the Fourier series coefficient. So how can we do that? The first thing that we need to do is we need to sketch a graph of this fx. And remember, this fx has a period of 2 pi. So class, we can sketch a function here. Okay, I write again, we have fx in the equation equal to 1 for x in between 0 to pi, and negative 1 for x in between negative pi to 0. So when we plot the graph here, okay, we have the angular frequency in this case is 1. Okay, and then we have a function here also negative 1. When x 0 to pi, the function is equal to 1. So you can plot a function 0 to pi, it is 1. And then when x in between 0 negative pi to 0. So here we have, for example, negative pi to 0. The function is equal to negative 1, means that it is somewhere here. Okay, so this is our graph, but we know that it is repeated for 2 pi period. So after 2 pi, it will repeat the same pattern, means that here up to 2 pi, you can see you will have a repetition pattern here. And then for this one up to negative 2 pi, it will repeat this one. Okay, so you will have this graph. So this is a graph of a function of fx and x for this question. And next class, you need to find a Fourier series. How to find a Fourier series? Remember, to compute a Fourier series, you need to find the coefficient of the Fourier series a naught, an, and also bn. We start here with this a naught. A naught equal to the formula of 2 over t. You have to integrate, start from negative t over 2 fx dx. So here we use fx dx because our function in terms of x. And then if you still remember in chapter 2, based on, in week 12, based on this one, the period, it is equal to 2 pi. And then our fx is given by the function of, in the question we have 1 for x in between 0 and pi, negative 1 for x in between negative pi and 0. So now class, for this one, when we want to solve this, you will have a naught equal to 2 over t is 2 pi, so 2 over 2 pi. You will integrate, start from negative t, okay, so negative 2 pi over 2 or 2 pi over 2 fx is given by this one, so I will not write it. First, I will write as fx first, but here, actually for this part class, if you forgot about this t, okay, you can only base on the domain here, on the range here. When we simplify this, we got 1 over pi. We integrate, actually start from negative pi to 0. Okay, negative pi to 0, fx is this value, negative 1 dx. Okay, this one you have to put all in the bracket. Okay, plus from 0 to pi, this range, okay, which is the function is given by 1 dx. Okay, when we solve this one, we'll got here 1 over pi multiplied by negative x, which is this x in between negative pi to 0, plus here you'll got x, which is start from 0 to pi. And then you can simplify this, which is 1 over pi, negative 0 minus negative pi, okay, plus pi minus 0. So here you will got positive, negative pi plus pi. We can cancel out this. So we got this one 0. All this will be 0 multiplied by 1 over pi. So you will got the answer 0 for our a naught. But class, it is not yet finished. You have another two coefficients to be solved. So the next one we'll see how can we solve for this an, and also the last one for bn. For an, we have the formula an equal to 1 over, actually 2 over 2 pi. So I simplify it. I can write 1 over pi, and then negative pi, we integrate start from negative pi to pi. We have fx, but this fx you need to multiply with cos and omega x dx. What does it mean by this omega? The omega here refers to the angular frequency, which is equal to 2 pi. We need to multiply 1 over t. So here 2 pi, 1 over period, 1 over 2 pi means that our angular frequency here equal to 1. Or in simple way, it is referred to the highest frequency of the positive fx. Okay, and then when we try to solve this one, we'll got here 1 over pi. You need to integrate negative pi to 0. So your fx, remember we have a function here. I write again 1 for x in between 0 and pi, negative 1 for x in between negative pi to 0. So here, negative pi to 0, we have negative 1. We multiply with cos, and omega is 1. So cos nx dx. And then we plus with integration start from 0 to pi. So this one 1 multiplied by cos nx dx means that you have to solve this integration. When we solve this integration class, we've got 1 over pi. Integrate this negative pi to 0, this one negative cos and x. Okay, negative cos and x. When we integrate this one, okay, integrate negative cos and x, you will got equal to negative sine and x per n. Okay, you integrate cos, you will got sine. Okay, you integrate in this cos of nx, you will got sine nx, and you have to divide by this n. Means that here we will have, this one will be negative sine nx over n, which is, it is from negative pi to 0, plus this one, okay, integrate cos nx, you will got sine nx over n, which is here from 0 to pi. And then when I can move this n, I can factorize this n, I will got here equal to 1 over n pi. Okay, negative sine of, I can substitute with this value 0 and negative pi here. Okay, we have negative sine of n times x. This is x. We need to substitute here. So negative sine 0 minus here negative sine. So minus negative, you got plus sine n times this one. This one you need to replace for this x, which is, you will got negative n pi. And then plus sine n pi minus sine 0. Okay, when we simplify this one, if you refer back to this important note here, sine negative n pi equal to 0, and then sine n pi also equal to 0. So I can substitute here, which is, this one is 10 to 0, this one also 0, means that for for an here, I write here, an we got equal to 0. Okay, so now we want to solve for bn. Formula is equal to 1 over pi. You need to integrate, start from negative pi to pi, and then your function here is fx multiplied by sine and omega x, but our omega is 1, so nx dx. In this case class, you will have your bn equal to 1 over pi. We integrate, start negative pi to 0. Okay, fx is negative 1. Multiply by, this one is 0, sine nx dx, and then plus 0 to pi, 1 times sine nx dx. Okay, this one and negative 1 is from equation. And then class, when we simplify this, when we integrate this one, we'll have 1 over pi. Integrate this one. Okay, it is negative sine and x. You integrate sine, you got negative cos. Means that negative cos and x. Okay, you will integrate. For example, sine and x dx here, you'll got equal to negative cos and x, which is over n. Means that in this case, we'll have this one negative, right? So when we integrate negative sine and x, we'll got cos and x over n, which is negative pi to 0, plus this one you will got here sine and x. So you integrate this, you got same as this one, which is negative cos and x over n, 0 to pi. And when I substitute 0, negative pi here, I will have 1 over pi cos 0. Okay, this n I factorize it. Okay, I move all this n outside. I have cos 0 minus cos negative n pi. And then here plus this one negative cos n pi. Okay, minus negative, so plus cos 0. When we solve this one, okay, this one you got 1, this one you got 1, means that you will have 1 over n pi 2 minus, okay, remember, this is actually even function. When even function, cos n pi will be equal to cos negative n pi. In this case, we can write this cos negative n pi as cos, this one equal to cos n pi. This is the use of even and odd function. So you have to understand about period, angular frequency, even and odd function from week 12 to solve full range Fourier series. So when this one equal to cos n pi, means that I will have here cos n pi minus, okay, because this is positive, negative, cos n pi. In this case, I can simplify. I will have 1 over n pi, 2 minus 2 cos n pi. So class, I can write this one as 2 over n pi, 1 minus cos n pi. But it's not yet our final answer. For this Bn, we need to form a table. Okay, and that we solved previously equal to 2 over n pi, 1 minus cos n pi. So class, in this case, when we want to find a full range Fourier series, you need to form a table. The first column is n, and then the next one is bn, and then the answer for this bn. Okay, the answer for this bn. Our n here for this one, n equal to 1, 2, 3, and so on. Okay, if you still remember the Fourier series formula. So this n, 1, 2, 3, 4, 5, and so on. When n equal to 1, means that when this n, we substitute with 1, we have here 2 over pi, 1 minus cos pi. And then cos pi is equal to negative 1. Okay, so we'll have here 2 over pi, 1 minus negative 1, means that I will have here 4 over pi times 1. Okay. This one is 2. I just write like this first. And then when n equal to 2, we substitute this n equal to 2. We have here 2 over 2 pi. Okay, because n is 2 now. And then 1 minus cos 2 pi. Okay, this one you can refer back to important notes from previous slide. And then cos 2 pi actually class is equal to this one equal to 1. Means that we'll have here 1, or I can write 2 over 2 pi, 1 minus 1. So in this case, I will got 2 over 2 pi times 0, that is equal to 0. When n equal to 3, so this is n equal to 2. When n equal to 3, we have here 2 over 3 pi. 1 minus cos 3 pi. And cos 3 pi class, when n is equal to 3, it is equal to cos pi. This is will go to negative 1. Means that we will have here 2 over 3 pi times 2. That is equal to 4 over 3 pi times 1. And then when n equal to 4, when you substitute, you will got 0. When n equal to 5, you will have here 2 over 5 pi. 1 minus cos 5 pi. And this one again goes to negative 1. Means that in this case, you will have 2 over 5 pi, which is times 2, that is 4 over 5 pi times 1. You can see it will have a same pattern. This one 0. For even number, you got all 0. You'll got all 0 if you repeat the same procedure. But for odd number, when n equal to odd number 1, 3, 5, and so on, you'll got 4 over n pi times 1. Okay, so in this case, our Bn will be equal to 0 if n equal to 2, 4, 6, and so on. And Bn will be equal to 4 over n pi. Okay, remember class, this one actually 1 pi and n is 1. This one 2 pi. Okay, this one, this one 3 pi and n equal to 3. This one 5 pi and n equal to 5. Means that here it is not negative class here. So 4 over n pi for n equal to 1, 3, 5, and so on. In this case, when we write our Fourier series, remember class, a Fourier series formula is come from this slide. Okay, this is ft, but we have question fx, so we change t to fx. In this case, a0 and an is equal to 0. When we substitute, we already find the coefficient for this Fourier series. A0 and an equal to 0, only we have here bn. Means that our Fourier series in this case will be equal to, okay, we can write our fx equal to the sum of n equal to 1 up to infinity, bn, and bn need to be multiplied with sine n omega t, or n omega x. In this case, we'll have here equal to, when n equal to 1, bn is 4 over pi sine and 1 omega also equal to 1, so sine x. Okay, and then plus, when n equal to 2 here, okay, n equal to 2, so we will have here bn is 0, so plus 0, plus n equal to 3, we will have here 4 over 3 pi. So 4 over 3 pi sine 3x, because here n is 3. And then when n equal to 4, okay, 0, bn is 0, so plus 0, and then plus 4 over 5 pi, this is n equal to 5, sine 5x plus 0 plus dot, 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 okay, up to infinity. Which is, when we simplify here, we have bn equal to 4 over pi, and then sine x plus 1 over 3 sine 3x plus 1 over 5 sine, this is plus, okay, sine 5x plus so on. So this is the full Fourier series for this full range function. Okay, this is the Fourier series for this function. Means that class, in summarize here, when you want to find the full range Fourier series, you need to find the coefficient of the Fourier series. Remember, you have the formula which is given by this ft. Okay, you have a0, an, and bn. And to find the full range Fourier series, you have to find a0, an, and bn by using these three formulas. In finding this, you need to know about the integration. We have first example a simple function. Maybe we can have a complicated function, maybe some function you need to use, for example, integration by part. So we go next for the next video on how to find a Fourier series for more complicated function. The video part 1 for this week is end here. I will show you more example on how to find a Fourier series in the next video. Thank you class for your attention. See you in the next video.